Hello, my name is Rob Purcell, and welcome to the Introduction to Breault Research Organization's Apex Introductory Tutorial. Today, we'll be going over some of the basics of Apex before even getting to the software itself, so feel free to sit back and follow along. So first off, what is Apex? Apex is one of Breault's optical modeling tools. What's special about it is not a separate program, but an extension to SolidWorks. This means you get the combination of Breault's optical design tools with SolidWorks CAD tools, all in one place. Apex comes with accurate optical components and sources already available from its catalog. This, plus the fact that mechanical design is done using well-known software such as SolidWorks, saves time and effort when it comes to optical modeling and prototyping. Breault has come up with a simple 4-step process for Apex that can be applied to any task and will be used in future examples. These 4 steps are designing and verifying geometry, so mostly SolidWorks and CAD, but there's a little bit of Apex in there as well. Designing and verifying sources is the next step, which is where Apex mostly comes in. Tracing the rays, and finally performing analysis on the system. These 4 steps will be shown in detail when examples come up later. Since you will have access to both SOLIDWORKS and Apex tools, it's good to know when to use what. For example, you can use SOLIDWORKS tools to sketch surfaces or create paths for light to travel, while using Apex tools to generate sources, lenses, or specific optical surfaces. The end goal is to create a ray trace ready model that you can use for optical prototyping and analysis without having to switch between optical and CAD software. It's all in one package. Apex sources are made to accurately represent both the radiometric and geometric parts of the source. This means source models can be of varying wavelength as needed, be it UV, visible, infrared, or what have you, while also working as an accurate representation of an actual source. Apex doesn't just generate an ideal source or a point source, since those are the easiest to model, but instead simulates common and coherent sources to conduct realistic modeling and ray tracing. To conduct this optical analysis, the geometry can be modeled using SOLIDWORKS or Apex tools, but then given optical properties through Apex, such as setting its index of refraction, dispersion, scatter, or coating. For example, you can make a simple surface using SOLIDWORKS, such as a plane or a cone, and make it completely reflective, and the Apex sources and ray traces will reflect off that surface. This is what makes Apex so powerful, as anything you can do in SOLIDWORKS can then be modified to be used for Apex-specific work. Optical modeling is an important step when designing illumination systems. Ray tracing with Apex allows you to model the flow of energy through a system before constructing it, allowing you to figure out the best design before investing time and effort into a real prototype. Now, an important concept to understand here is radiometry. If you know optics, you know radiometry is the measurement of radiant energy, in simple terms. In Apex, this is represented through the calculation of radiant energy from the rays and beams, while also taking geometry into account, both the geometry of the system and the geometry of the rays itself. This will be useful for the analysis of any modeled optical system. Now to cover some of the basics of SOLIDWORKS and CAD. In SOLIDWORKS, there are a few different levels of a system to consider. At the highest level is assembly. An assembly is a combination of all the smaller parts and subassemblies into one file. Essentially, it is where you assemble all your parts into one completed design, hence the name. A level lower than that is parts. Part files are your individual components that you made using features. For example, if your assembly is an illumination system, your parts might consist of a reflector, a target, and a source. The level underneath that is features. Features are the individual design elements of a system and can be split into 2 groups. The sketched features are formed using the 2D sketch of a part. For example, you can extrude, revolve, or sweep a sketch to make a solid object from a line. Applied features are features that can only be used on a solid object. Once you've used some sketch feature to create a solid object, you can then use the applied features to modify it further. These include chamfers, fillets, holes, to name a few. The Feature Manager design tree in SOLIDWORKS will allow you to quickly see all features and components of a part or assembly without having to find it in the physical model. Keep these terms in mind, as it'll make sense once we get to some actual modeling. As mentioned previously, parts are made up of sketches and features. Sketches are used to define the basic shape or outline of the part, and are made up of lines, rectangles, arcs, and is in most cases 2-dimensional, on a specific plane. Features are the shapes that come from the sketch to form the part. Bosses and bases add material, while cuts remove material from the shape. Here is a sample SOLIDWORKS and Apex window. Specifically, this is a blank part file. Here, we have pointed out some of the more important things to be aware of to get used to some of the terms that will be used when discussing SOLIDWORKS and Apex. These will be explained in depth in the following slides. To start, the Command Manager. The Command Manager is one of, if not the most important tab to be aware of, as that's where most of the work can be done. You can click through the tabs to find all the different options of what you can do. It can also be customized, adding or removing tabs you find necessary or unnecessary. Also, the tabs will change depending on if you are in a part or assembly file, with a few Apex-specific ones as well. In a part file, the Apex tab is titled Optical Geometry, while in an assembly file, the Apex tabs are Project Settings, Optical Geometry, Sources, Trace, Analyze, and Design. The confirmation corner is where you can commit or cancel changes made. Depending on whether you are editing a sketch or using some other command, the corner will look different, but still essentially operates the same. Click Yes to save it, click No to stop any changes from being made. The Heads-Up View toolbar will let you adjust how you are viewing your project. The buttons from left to right are Zoom to Fit, which zooms the project to fit the window, Zoom to Area, which zooms to a selected area, Previous View obviously returns to the last view, Section View lets you cut into your project to get a sectional view, View Orientation changes the view to any of the pre-selected default views, Display Style changes the visual style of the project without changing the geometric properties, such as having it appear as a wireframe, and Hide Show Items lets you hide or show previously hidden items. The other buttons allow you to make various cosmetic changes, such as changing colors, including the background. Like I said, View Orientation sets the view to a pre-selected orientation. These orientations are isometric, trimetric, dimetric, top, left, right, front, back, bottom, normal to, single view, two view, and four view. You can also rotate the view manually by holding down the middle mouse button and moving the mouse around. The Display Style button has 5 different options. Shaded with edges, which is the default setting. Shaded, which makes edges less obvious. Hidden Lines Removed, which shows only the currently visible edges. Hidden Lines Visible, which shows all edges in the system, with hidden edges represented as a dotted line. And Wireframe, which only shows the edges and not the geometry itself. These, along with being able to hide or change the transparency of items, are good ways to look at specific or hard-to-see parts of your project without having to disassemble it. The status bar at the bottom tells you your current X, Y, and Z position in the window, as well as if your design is under, over, or fully defined. It also tells you what you are currently editing, as well as if your project needs a rebuild. The reference triad points out the X, Y, and Z directions. If you click on the different directions of the triad, it will snap you to that view orientation, and clicking it again will flip it to the opposite, i.e., clicking the X arrow will put you in the right view orientation, and clicking it again will flip it to the left view orientation. Below the triad, it will tell you what your current view orientation is, as long as you are on one of the standard orientations from before. The Feature Manager design tree is where all your features, sketches, and parts can be found in a list format. From here, you can select anything without having to find it physically in the model, which helps for smaller or harder to reach parts. You can also scroll through and find the Apex Optics Manager, which, as you can probably guess, will be important for a lot of the Apex work you will be doing, especially analysis. From the Optics Manager, you can find the optical libraries for lenses, sources, coatings, media, and more, as well as any optical properties that have been applied to any SOLIDWORKS construction. There's also a tab for any analysis that has been done, ranging from ray trace sets, irradiance measurements, and spots diagrams. The Analysis tab only shows up in assembly files, however, not part files. The sketch origin is self-explanatory, as it is the origin, or intersection point, of the X, Y, and Z planes. You can use the origin as a reference point when defining relations or mates. Dimensions and relations are very important in CAD. Locking down the specific size or shape or angle that a part has helps to fully define a project. It can turn into a real issue if you don't fully define all the dimensions of a model or part, which is why the first step in the 4-step process is to define and verify geometry. Mates establish how parts interact in an assembly. There are several different types of mates to help solidify your assembly. For example, you can have a distance mate between two parts so that they are always a set distance apart from each other, or the opposite, a coincident mate to make sure two parts stay connected. Using mates and relations is how you slowly remove degrees of freedom from your model, ideally getting to a point where it's fully defined with no loose parts. When you press the Help button in SOLIDWORKS 2024, as long as you are connected to the internet, you will be taken to their online web help page. If you have Use Web Help turned off in the Settings menu, you can open the local In-Software Help menu, which lets you find tutorials for various SOLIDWORKS tools. Some of these help pages have videos showing specifically how to do something. If you see a link titled Video or a little camera icon, that should lead to a help video for that topic. When it comes to optical modeling, having a proper model leads to accurate simulations and test data. Combining optics and CAD in the same program makes this easier and helps save time and money in the long run. Here are some basic optics terms that are good to at the very least be aware of while modeling. If you come from the field of optics, these should all be at least somewhat familiar, but if you're more of a CAD person, I would recommend looking into these to at least get a brief overview of some of the important optics concepts. We'll go over a couple of them right now. Refractive index is the most important optical property to be aware of. The refractive index of an object changes how light bends when it enters the new medium. The refractive index in a vacuum is 1, and it goes up from there depending on how much a material causes light to refract. Other important optical properties to be aware of include dispersion, transmittance, and reflectance. These properties and their values are what optical modeling is all about, meaning not only is the geometry of a system important, but the material it is made of as well. Light rays in apex are defined by a few different parameters. These include starting position, propagation direction, flux, and wavelength. Rays represent potential light paths, as well as the flow of energy in a system. When a light ray hits the surface, not only will the direction of travel change due to refraction, but also the energy in the ray will change due to Fresnel effects and absorption values. You can calculate the direction a ray will travel after hitting a surface using Snell's law if you know the refractive indices of both mediums. This works backwards too. If you know the ray path and at least one refractive index, you can find the unknown index as well. When light is reflected, the incident or incoming angle is equal to the reflected or outgoing angle relative to the normal at the point of intersection. For example, if you send a laser beam in an ideal planar mirror at 45 degrees, the beam will then reflect at an angle of 45 degrees from the opposite direction. And that concludes the introduction section of the Apex intro. Up next, we will be doing the first bit of actual modeling, where we will design and analyze the system shown. Thank you so much for watching.